Good morning, ladies and gentlemen. Welcome to this video on logarithmic functions and how we graph them. But before we continue, I'd like to draw your attention to exponential functions. So recall, the most classic exponential function we probably see is this one here for exponential growth, and that occurs when a is greater than 0, when we have that form of equation. Alternatively, a is between 0 and 1, we get this sort of decrease. If a is 1, it's horizontal, and a can't be less than 0. Alright. Note a few things about this. First of all, the domain is real. We have all domain. The range is strictly positive, and there is a horizontal asymptote at y equals 0. Now, let's look at an inverse. So, to calculate the inverse, or to visualize the inverse, you imagine a reflection about the line x equals y. So, a reflection about the line x equals y is if we draw a line that goes through. It's a terrible line. That's closer. So the line x equals y goes through the point 1, 1, 2, 2, 3, 3, 4, 4, etc., where x is equal to y. And if we want to show a reflection in this, well, we can consider points on the original graph, which is y equals 2 to the x. So original points in this graph, y equals 2 to the x, is minus 2, a quarter. Minus 1, a half, 0, 1, 1, 2, 2, 4. We get that beautiful curve. The reflection, or log base 2 of x, the inverse, has a quarter minus 2. A half minus 1. 1, 0. 2, 1. 4, 2. We get exactly the same curve as this. It's just reflected about the xy axis. So there's a line, you get this, but mirror imaged over to the other side. So a few properties that come from this reflection. This distance and this distance, this distance and this distance, they will always have an equal opposite distance. That comes from just the reflective properties. Note that the domain and the range swap. So originally, we had a positive range, strictly positive. Now, in our green function, we have a strictly positive domain. Originally, with y equals 2 to the x, we had a real domain. Now, we have a real range. Originally, we had a y equals 0 horizontal asymptote. Now, we have an x equals 0 vertical asymptote. Essentially, this happened. Domain, range, switched, x and y in all cases. And what we've shown, sorry I'm running around a bit here, what we've just visualized is this. And that works for all exponential and their log equivalents. Although some of them will still show the reflection, but it comes up looking like this because of the way the original graph is. Alright. That gives you a basic idea of the properties of a log graph. Please copy these down carefully. Note the different points or values. Note those properties. And now I'd like to finish off by doing a very brief problem. Exponential modeling. So not actually involving log graphing, but you could graph it using logs if you like. Now this here is worth knowing because it asks you to increase something by a percent, and it asks you to do it repeatedly, compounding annually. So to increase something by 4.8%, you multiply by 1.048. If you multiply by 1.048, it increases it by 4.8%. It's basically converting this into a decimal, so divide by 100, then adding 1 to it. And that works with any percentage increase problem. What this here is saying is if you have $10,000, that is multiplied by 1.048 to the power of n. N meaning that's happening many times annually, so how long? And that's equal to 15,000. Alright. Then, what we have next, excuse me, I really need a pen, is we can divide both sides by 1,000. So 1.048 to the n equals 1.5. Then we're going to take the log of both sides. So n log 1.048 equals log 1.5. And I've dropped the n down to bottom out the front of the log, but you could show that in 2 steps if you want. Then your final step is n is equal to log 1.5 over log 1.048. Apologies for the quality there. That you can just throw in your calculator to give you the solution. Alright, quick video, but hopefully you've got some basic notes of the idea of an inverse and that logs are inverses of exponential functions.